Alright, so this is going to be about functions. And remember, functions is just a relationship where each input, which we usually use the variable x, has a single output, which we use the variable y. And functions are usually represented many different ways. And I think this is where hopefully everything kind of comes together and it kind of makes sense after this little video. First of all, how they are represented, and I just picked the table just for starters to begin with. So a lot of times we'll see a table. Table can be horizontal or it can be vertical, and it goes with just what the saying is each input has exactly one output. So, it doesn't always have the x or y. You can use different variables, but in most cases you see x and y. But if it is a horizontal, the top one would be the input, the bottom one would be the output. And sometimes they even put words in there as well. And all you have to do is literally look to see if any of the inputs are repeated, and you can see these are not. So right now, this table represents a function. Okay? Each input has exactly one output. Now, if we look down here, 3, 4, 5 are our inputs, and it's okay to have multiple outputs that are the same, because that does not go against the definition. Over here, 2, 4, 6, 0, negative 2, negative 4. So again, we look at all our inputs, and all of these are representative of a function. Okay? Equations. Now, when we get into equations, that goes into linear and nonlinear. This year we focused with our equations almost exclusively as linear, but then we did have a part where you had to identify the nonlinear equations. And remember, our slope-intercept form is the model for a linear equation. Again, we have our input and we have our output represented with our x and y's. M and B, slope and y-intercept, we'll get into that here in a little bit later. But right now, remember, linear equations are any equation that have two variables, and it could be written many different ways, and it just has to be where there's two different variables, and these would be linear. And you can also have just x equals 5, that is linear. Remember, x equals 5 is, well, actually that would not be a function, but it would be a linear equation. And then y equals 5, that would be a horizontal line, and that would be a function, but it would be also linear. So then you get into the question, is it linear, nonlinear, a function or not a function? And I think that's where a lot of people got confused. So remember, nonlinear equations, there are a couple of things that we have to remember. Number one, y equals 2x plus 5. Remember, the x can't be a denominator, and another common one is y equals 2x squared plus 5, where x cannot have an exponent. So basically, if you have an exponent, unless an exponent is with that, because that's, remember, 25 is the only time that you would want an exponent. So linear and nonlinear, so equations. And again, they can either be linear or non-linear. But again, this year we focus mostly on linear equations as functions. So how do equations and tables relate? Well, you can have an equation, and it can be written any way. I'm going to just put like this. And you're like, oh crap, that looks strange. How do I figure out what this is? Now again, we don't have any context, so the 2x plus 5 equals 3y is irrelevant, but we can still figure out a table. Now what I would suggest to most people is to put it in slope-intercept form, where you have your output isolated, and then that makes it a little bit easier. And again, that's where you go through and change that. And I'm gonna cheat a little bit and make that a 6, just to make it a little easier. And then to put it in slope-intercept form, remember, all of this is here, so I just have to divide by 3 And then I'd have 2/3 x plus 2 equals y. Now that's in slope-intercept form. But how that works is usually when it's in slope-intercept form, you can figure out the table. So then you have your input and your output. And I'm going to make this a little bit easier. Since I see my input has that, I know anything that is a multiple of 3 is going to make a nice even number. And again, depending on the situation, which I'll show you at the end, you can choose your inputs based off of what the situation is talking about. So we want our functions to represent a real world scenario, and then it makes a lot more sense than just throwing up random numbers. But let's just say 0. And we should know what our answer is, because remember, 0 as an x is always going to be our y-intercept, so that's going to be 2. And that means I would just put 0 into the equation, and then I'd do the calculation. So 2/3 times 0 is 0 plus 2, so that would be 2. So my answer, so this would be 0 plus 2 equals y, 2 equals y, so that's where I got my 2 there. So now let's try another one. Let's try a 3. So 2/3 times 3, and this is where I input it into the equation, and then I can do the calculation. Cross cancel, 2 plus 2, 4, y equals 4. So when my input is 3, my output will be 4. Oh, we remembered about the change in x and change in y. So I can just do this. I can add 2, and I can add 3, and since this is linear, since we know it's linear, I can follow this pattern here and just fill in the gap and make a table really quick that way. Now those are, I can come up with the numbers for 2 and 3, but our y's are going to have fractions in them or decimals depending on how you convert it. But that's an easy way to fill out a table. Again, tables and equations usually correlate with a real world scenario, which we don't have right here. It's just an example. So that's how equations and tables kind of are related in the function world. So that leads to mapping. Now mapping is just ordered pairs isolated in inputs and outputs. And the left is always the input, the right is always the output. And the key is always, remember function, each input has exactly one output. So then it just lines to here. So 5 goes with 9, so that's my ordered pair. 5, 9, so that could be put on a graph. 5, 9, right there. 6 goes with 10, 6 and 10. So 6 and 10 would be right there. Oops, my bad. 6 and 10. And then 7 and 8. So 7 and 8. So 7 and 8 would be right there. And you can see this would be a non-linear function, but it is a function because each input has at least one output. Our next map, sometimes we use boxes, sometimes we use circles. We can look right here with our input 6 as a 6 and a 3, 6 and a 7. Right there, the 6's are repeated, and therefore that means there is more than one input with 6, so therefore this is no fun. Not a function, no fun. Graphs. That's where we have linear versus nonlinear, and this is where we can use the vertical line test. So remember, when we are on a graph, you have your x-axis and your y-axis. So x-axis will be, if you have the same x, when you put them all together, we'll make a vertical line that goes up and down, right? Which is vertical. So you can see right here with this line right here, I can make vertical lines. So I'm going to use the y-axis, and it only crosses once. So then I can make more and vertical lines, and I can see that it only crosses once. So this is a function. That's fun. Now we got a little squiggly, not a straight line. So this would have a different type of equation that would match our non-linear equations that we learned. So it probably has an exponent in there somehow. And again, we can do our vertical line test, and you can see it only crosses at one spot. So this is a function. Okay, that's the easiest thing to do on graphs. And then anything that's an enclosed or anything that comes across by itself is no fun, not a function. Okay? So if you have an enclosed shape, but again, if you have something like they like to do problems like this, you can see right here and right here just with the y-axis that crosses more than once. So let's just say this point here is what would that be? 0, -2. Let's say this would be like 0, 2. And any way you look at it, my x values both have 0. So therefore the 0 is being repeated. Therefore it's no fun, not a function. Okay, word problems. Now this one's going to get a little lengthy. Now this is going to make things a little more sense in terms of input, output, and things like that. And this is like your vocabulary task for Monday, and something I tried to teach you guys throughout the year is the independent variable and dependent variable. Now I didn't talk about the domain and range. Domain and range are, remember, just other ways. Domain is just the values for x, and range is the values for y in our ordered pairs. But then we get into independent variable and dependent variable. These aren't numbers. These are descriptors of the numbers that we will be using. And what we have to do is we have to read the word problem, and right here is Joe makes $5 per hour mowing lawns. He charges a showing up fee of $10. So the ultimate question is, which I forgot to write down, is how much money does he make when he works blank hours? So the amount of hours that it takes for him to mow a lawn will range. You know, the size of the lawn, if there's a bunch of trees in the way, things like that. So there's a lot of variables. So he charges just $10 to show up, and then it's $5 per hour. And I'm going to talk about those two numbers. But what we have to think about is our independent variable and our dependent variable, which will, once we start coming up with an equation, will describe our input, and then once we get our answer, we'll describe our output. So I always like to do the dependent variable because that's your outcome. What do you want to achieve? Well, if I'm Joe and I'm mowing lawns, I want to know my money. How much money am I going to make? So that could be my descriptor, total money earned. Okay, so after each job that Joe completes, he wants to know how much money he makes. His independent variable, well, what is going to determine how much money that he makes? And again, that's how many hours that it takes him to mow the lawn, or hours and minutes and things like that. So that is, we can put number of hours, just to make it simple, number of hours that he works. So 2 will be his input if he works 2 hours, and his output will be whatever that is based off of that. But we're trying to write an equation here still, but we got there's two numbers inside, and that's where it comes to where our slope, which is our rate of change, and then our starting point, or where do we begin? So we got to look at this. So I see and it's important to remember $5 per hour, and I see a startup fee of $10. Well, startup fee, well, that's just showing up. So that's a one-time fee. So even if he doesn't mow, just for showing up. So if I call up Joe and tell him to come to my house, just showing up to my house, I owe him $10. He didn't mow, he didn't do any work. That's just his fee to come out. So the starting out fee is $10. His rate of change is, again, that's going to go into relation to the input, and you can see hours and hours. So those kind of relate. So if I work multiple hours, I can multiply. And remember, when we go to slope intercept, it's y equals mx plus b. So we're going to multiply our rate of change, or also known as our slope, times our input, which is explained to our independent variable, which is the number of hours. So our rate of change is simply $5. And then we could put per hour. So every hour I work, I make $5 if I'm Joe. 2 hours would be $10, etc. But remember, you got to include the fee. So let's go to this problem in a little bit. So what's our equation going to be? So what's our equation going to be? Well, we know X is going to be number of hours. Our Y is going to be our total money. Our M is going to be $5, and our B is going to be $10. So now all I have to do is put it in Y equals MX plus B and just fill in the gaps. Y equals M is 5 times X, so that's our variable, and then that's plus 10. So this is how the equation and the table come into play. So maybe Joe doesn't want to do the calculation every time, and he just wants to have one little area. And actually I can add a graph to this too. So let's do a graph as well. So on our table, so this is our X, so that's our number of hours. And this is our Y, which is money earned. And then I can also do that in the graph where our Y is money earned. And our X is our number of hours. So you see how they're all related? And they all get tied up with our X and Y and our M and our B. So let's go to this. So if I work 0 hours, I can put that into the equation. So 0 hours, I get paid $10. So right here, 0 hours would be 10. Okay? Y-intercept, right? So then I know every hour, if I work 1 hour, if I work 1 hour, I put 1 in for there, and I can do the calculation. And 1 hour is $15. So I can go 1 hour, and then that would be 15, and that would be right here. 2 hours. Put a 2 in here. 10 plus 10 is 20. And we can kind of see this because it's linear, so we can see the graph and the table kind of correlate. But let's just say, all right, that's kind of basically what he does. And you can put 2.5 hours and 2 hours and 15 minutes and things like that and do those calculations as well. But let's just say, Joe's like, God, I had to mow this big park, and it's going to take me like at least 5-6 hours. So he just wants to guess. He wants to get kind of an estimate about how much he's going to make if he has to work like 5 hours. So then he could put a 5 in, and then I can just go up here and put 5 times 5 plus 10, 25 plus 10, add those together. So if I worked 5 hours, which means number of hours, and then after I add my startup fee and my hourly rate, once I put those together, I make $35, which is my Y, which is my outcome, and I make $35 in those 5 hours. Not a bad day's work for Joe, working and mowing the lawns. So that's how functions are all represented. Now the last thing I want to talk to you guys about is proportional relationships. Proportional relationships means when I'm on a table or a graph, so let's just do a table, everything, it didn't work out. My bad. I goofed up on that. Ignore that. A proportional relationship will be where everything goes the same for the increments. So, for example, they all always have to be 0, 0. So if I go up 1, this will go up 2. This goes 2. This has to go 4, 6, and whoops, my bad, 4, and then this would be 6. So you can see that would be 6. My bad, 3 would be 6. So these are all going up 1, and these are all going up 2. So remember, our slope is 2 over 1, and that means that all of these are 2 over 1, so they would all be the same. Now here, this goes up 10, and this goes up 5, this goes up 5, and then this goes up 5, so therefore, you see it doesn't match. So I'd have different rates on that, so it wouldn't be proportional. So that's that. So that's our proportional relationship. Proportional relationships will always be y equals like 2x, and then they will always go through the origin. Okay? Kind of goofed up that last part, but you guys get the gist of it. Have a good one. Bye.